Everyone's seen a Sherman tank, but almost no one has actually understood what it was like to crew one. You've seen the footage. Black and white reels of tanks, rolling through bombed-out towns, dust clouds rising off dirt roads, crews hanging off the hulls like they owned the place. It looks almost heroic. Clean, even. Hollywood spent decades making it look that way. But here's what those reels never showed you. The inside of that tank, the smell of burned propellant baking in 90-degree heat, the rattle of machine gun fire hitting the hull like someone threw a fistful of gravel against a tin shed, the way a crew of 5 men crammed into a metal box the size of a walk-in closet, sweating through their uniforms, trying to figure out if that shadow at the tree line was a bush or an 88mm gun about to ruin their entire afternoon. And most importantly, the thing they did to try and stay alive. The thing that looked bizarre from the outside, but made complete and total sense to anyone who had ever sat inside one of those machines and thought about what happened when a German anti-tank round hit the side. They welded spare track links to the hull. Not as decoration, not for some mechanical reason, but because American tankers had looked at their own vehicles, looked at the enemy's weapons, done the math, and decided they were not going to sit inside a thin-skinned steel box and hope for the best. If you've ever looked at a photograph of a late-war American Sherman and noticed what looked like extra armor bolted, welded, or strapped to the outside, you were looking at improvised crew survival. You were looking at the answer to a problem the Army didn't fully solve in time. And you were looking at one of the most fascinating, most human stories of the entire Second World War. Because this isn't just a story about metal. It's a story about what happens when men realize that the people in charge of building their equipment made a miscalculation, and then those men decide to fix it themselves. Stick around, because what those tank crews did, why they did it, and what it tells us about the reality of armored warfare in World War II goes a lot deeper than spare track links welded onto steel. And if you want more stories like this, real history, real detail, none of the sanitized version, make sure you subscribe right now, because we go places the textbooks don't. Let's start at the beginning. Not with tanks, not with armor, not with Germany. Let's start with a question that seems almost too simple. What makes a tank a tank? Most people would say armor. The whole point of a tank is that it's protected, right? You put men inside steel, they can survive things infantry can't. They can move through fire, advance under shell bursts, hold ground that would shred a squad of soldiers in seconds. That's the theory. That's the sales pitch. But armor isn't magic. It's physics, and physics doesn't care about theory. What actually protects a tank isn't just how thick the steel is. It's a combination of thickness, angle, hardness, and what kind of round is hitting it. A round that strikes at a steep angle is more likely to penetrate than one that hits a sloped surface and deflects. A shaped charge works completely differently from a solid kinetic penetrator. A high-velocity rifle-caliber round bouncing off is a completely different situation from an 88mm projectile traveling at 900 meters per second. Tank armor in World War II was a constant arms race. Every time one side made a better tank, the other side made a better gun. Every time one side made a better gun, the other side added more armor. It went back and forth like this the entire war. And the Americans, for most of the conflict, were on the losing end of that race, in one very specific place. The Sherman. The M4 Sherman medium tank is one of the most produced and most recognizable tanks in history. More than 49,000 were built. They were given to American, British, Canadian, French, Polish, and Soviet forces. They fought in North Africa, Italy, France, the Pacific, the Philippines, and half a dozen other theaters. In sheer numbers, the Sherman was everywhere. And in sheer numbers, that was exactly the American strategy. Build them fast. Build them in quantity. Lose some. Replace them. Keep moving. It was a philosophy that made sense from a logistics standpoint. American industrial capacity was staggering. The idea was that even if the Sherman wasn't the best tank on the field, there would always be more Shermans. What this philosophy missed, brutally and tragically, was that inside each one of those replaceable Shermans was a crew of 5 men who were very much not replaceable. The Sherman had a crew of 5: commander, gunner, loader, driver, assistant driver. 5 men in a steel box, working in tight, almost unbearable conditions, trusting that the walls around them would hold. And the walls, in too many encounters, did not hold. The Sherman's armor ranged from about 12 millimeters at its thinnest to just over 60 millimeters on the upper front hull in later variants. The hull sides were thinner, the hull rear was thinner still, and the early models had a serious problem that went well beyond just armor thickness. They burned. Early Shermans stored their ammunition in the sponsons, the wide shelves on either side of the hull interior, right next to the crew. When a German round penetrated, it could ignite those ammunition racks and turn the inside of the tank into an inferno in seconds. German tank crews and infantry started calling the Sherman the Tommy Cooker. British crews called it the Ronson, after the cigarette lighter whose advertising slogan was, "Lights every time." Neither nickname was a compliment. The Army worked to address the ammunition problem, eventually moving to wet stowage, where ammunition was surrounded by a water and antifreeze mixture to reduce the risk of fire. Later production Shermans were significantly better than the early ones. But the fundamental problem, a medium tank designed for mobility and mass production, facing enemies whose primary anti-tank weapons could punch through its sides at combat ranges, never fully went away. And the men inside those tanks knew it. This is where you have to understand something about the psychology of armored warfare. When you're inside a tank, you know what your vehicle can and cannot do better than any general, better than any engineer who designed it, better than any politician who signed off on the contract. You know it in your gut. You know it every time you button up the hatch and hear that lock click shut. You are inside a machine, and if the right round hits the right spot, that machine becomes your coffin. American tankers, in the European theater, saw what German guns could do. They saw it to their friends' vehicles. They heard the horror stories, from Tunisia, from Sicily, from the fighting around Caen. They arrived in France after D-Day, knowing that the German Panzerfaust, the Panzer IV, the Panther, and especially the Tiger, were all capable of killing their vehicles. So they did what soldiers have always done when they believe their equipment isn't quite good enough. They started modifying it. Now let's talk about the track links specifically, because this is where the story gets genuinely interesting and where the physics becomes really important. A Sherman tank runs on tracks. Those tracks are made of steel links, connected together to form a continuous loop around the road wheels and drive sprocket. Those links are roughly rectangular chunks of steel, maybe 3 or 4 centimeters thick, designed to handle the weight and stress of a 30-ton vehicle moving over rough terrain. They're heavy, they're dense, and they're lying around in abundance on any armored unit. When a tank loses a track, or when links get damaged, worn, or replaced, the old ones don't disappear. They sit around. They pile up. And at some point, some tanker, probably lying awake in his cot, thinking about German 88s, looked at those spare track links and had a thought. What if I put those on the outside of my hull? It seems almost too simple. And in a way, that's the beauty of it. The logic goes like this. If an anti-tank round hits a steel plate, it penetrates, if it has enough energy, and the plate isn't thick enough. But if you add another layer of steel in front of that plate, 2 things can happen. Either the round loses enough energy hitting the first layer that it can't fully penetrate the second, or the round deforms, breaks up, or tumbles after hitting the first layer, making it far less effective at penetrating the second. This is called spaced armor, and it's not just improvised soldier tinkering, it's real ballistic engineering. The principle had been understood and applied formally long before Sherman crews started bolting on track links. But here's the twist. Spaced armor works differently depending on what kind of round is hitting it. Against a traditional armor-piercing kinetic penetrator, a round that works by transferring mass and velocity into the steel plate, spaced armor provides moderate benefit. The outer layer absorbs some energy. The gap allows the projectile to destabilize slightly, and the main armor gets a softer hit. Against a shaped charge, spaced armor works extraordinarily well. A shaped charge doesn't work like a bullet. It doesn't punch through steel by brute force. Instead, it uses a liner, usually copper, and an explosive shaped behind it, to create a hypervelocity jet of molten metal and plasma that squirts into the armor at extremely high pressure. This jet is what actually penetrates, and it is devastatingly effective at penetrating solid steel. But shaped charges have a critical weakness. They need standoff distance. The jet needs to form completely before it hits the main armor. If something disrupts the jet early, before it fully forms, the penetration is dramatically reduced or eliminated entirely. Spaced armor does exactly that. By the time the jet gets through the outer layer and the gap, it has already spent some of its energy, expanded, and lost coherence. It still might penetrate, but with far less depth and far less behind armor effect. In the European theater in 1944 and 1945, American tanks faced a particular threat that made spaced armor immediately relevant: the Panzerfaust. The Panzerfaust was a German disposable anti-tank weapon, cheap to make, easy to use, deadly at close range. A single infantryman could carry one and knock out a tank. It worked by firing a large-shaped charge warhead on a simple stick, and it could penetrate well over 150 millimeters of steel at point-blank range. For a Sherman, whose side armor was often only about 38 millimeters thick, a Panzerfaust hit to the side or rear was almost certainly fatal. And in the bocage of Normandy, in the rubble of French and German towns, in the narrow streets of cities like Cologne and Aachen, where visibility was minimal and a single German soldier with a Panzerfaust could duck around a corner and disappear, this was not a theoretical threat. It was constant. It was everywhere. American tankers figured out that welding track links to the hull sides, sometimes covering the lower hull, the turret cheeks, even the front glacis, with additional layers of steel, gave them a fighting chance against exactly that threat. The track links, being dense rectangular steel blocks, provided exactly the kind of disrupting outer layer that a shaped charge warhead needed to defeat. Did it always work? No. Nothing in warfare always works. A Panzerfaust hit, at very close range on a direct perpendicular shot, still posed a serious threat. But extra armor increased the chances of survival. And when you're sitting inside a tank in 1944, any increase in your chances of survival is worth a tremendous amount of effort. Let's not romanticize this, though. Adding track links to a Sherman wasn't a quick 10-minute job. The links had to be acquired, positioned, and then welded on. Not every tank unit had convenient access to a welder. Not every situation gave crews enough time to do the work properly. In some cases, crews improvised with wire, straps, or just propped the links against the hull temporarily. In others, the work was done carefully at maintenance depots, with proper welding equipment and a methodical approach. The coverage varied from tank to tank, unit to unit, and theater to theater. Some crews focused on the hull sides, the most common direction of attack from Panzerfaust ambushes. Others added links to the front, worried about the lower hull, where angled shots might slip under the main glacis armor. A few tankers went further, adding sandbags, concrete, wooden planking, and other materials alongside, or instead of track links, depending on what was available. The results were improvised and variable, but they were also completely logical. These weren't men making random modifications out of boredom. These were professionals, doing a professional calculation and acting on it with the materials at hand. And that's actually one of the most important things to understand about this whole story. The fact that American tankers felt the need to do this at all says something profound about the gap between what they were given and what they needed. Now, let's talk about that gap more carefully, because the Army wasn't oblivious. The United States Army did not ignore the problems with Sherman armor. Complaints came in from the field almost immediately once crews started encountering German tanks and anti-tank weapons in numbers. Reports from North Africa in 1942 and 1943 highlighted the Sherman's vulnerability, particularly its tendency to catch fire when penetrated. By 1944, the Army had addressed the fire problem through wet stowage and redesigned ammunition storage. Later Shermans also received a thicker, more steeply angled upper hull, improving resistance against some threats. But the fundamental weight and armor constraints remained. Here's the problem. The Sherman was designed within constraints that seemed entirely reasonable in the late 1930s and early 1940s, American military planners expected the tank to fight in a combined arms role, working alongside infantry and artillery, using maneuver and numbers rather than trying to out-armor German tanks in a straight-up duel. The Sherman wasn't supposed to be fighting Panthers and Tigers one-on-one. It was supposed to be working as part of a larger tactical system. And to a degree, this philosophy wasn't entirely wrong. The real tank killers in the American arsenal were M10 and M36 tank destroyers, which carried larger guns, more capable of handling heavier German armor. The idea was that Shermans would handle infantry support and exploitation, while dedicated anti-tank vehicles handled German armor. But theory and reality have a nasty habit of diverging. In practice, tank destroyers couldn't be everywhere at once. Sherman crews ended up in direct engagements with German tanks and anti-tank guns constantly, and in those moments, the difference between their armor and the enemy's capability was painfully obvious. The Army did consider various solutions. There were proposals for replacing the Sherman entirely with heavier American tanks. The M26 Pershing eventually made it to Europe by early 1945, bringing a 90mm gun and much heavier armor. But it arrived late and in small numbers. For most of the European campaign, the Sherman was what the men had, and improvised modifications were one of the few options available to bridge the gap. Now let's step inside a Sherman for a moment, because you can't understand why the crews did what they did without understanding what it was like to be in there. The interior of a Sherman medium tank was, to put it generously, cramped. The tank itself wasn't small by any stretch, but pack 5 men, a radio, ammunition, weapons, tools, personal gear, food, water, fuel systems, and an engine into the same space, and what you had was barely controlled chaos. The driver sat up front on the left. He had a set of steering levers and throttle, and a hatch above his head. In combat, that hatch would be closed, which meant he drove by looking through a periscope, a small prism device that gave him a limited and distorted view of the road ahead. Next to the driver, on the right, was the assistant driver. His primary weapon was the bow machine gun, a .30 caliber Browning mounted in a ball mount in the front hull. He could traverse it a limited amount and fire it, but his field of view was narrow, and his ability to actually hit specific targets was limited. In many units, the assistant driver also became the de facto ammunition handler when the fighting got heavy. Behind them, in the turret, were the 3 most critical crew members for the actual fighting capability of the tank. The loader sat on the left side of the gun. His job was to grab 75mm or later 76mm shells from storage, load them into the breech, and get out of the way before the gun fired. It was physically demanding, repetitive, and in a hot action, absolutely exhausting. The loader had to keep track of ammunition types, select the right round for the target, and maintain a pace fast enough to give the gunner the rate of fire he needed. The gunner sat to the right of the gun and slightly forward. He aimed and fired. He had an optical sight, a traversing mechanism he operated with hand and foot controls, and the trigger. His job sounds simple. It was not. Identifying targets through a narrow optical sight while the tank was moving, while smoke was everywhere, while the commander was shouting corrections, while shells were potentially hitting the outside of the hull, while trying to judge range and lead a moving target, all of that at the same time made gunnery one of the most demanding skills in armored warfare. And at the top, in the cupola, was the commander. He was responsible for everything: navigation, target acquisition, communication with other tanks, and with infantry and artillery, tactical decisions, crew management. The commander typically fought with his hatch open so he could see better, which meant that while everyone else was buttoned up inside steel, the commander was partially exposed. The inside of a Sherman at combat was loud in ways that are hard to imagine from the outside. The engine was deafening. The tracks made a constant grinding, clanking roar. The radio crackled. The gun, when it fired, produced a concussive blast that you didn't just hear, you felt in your chest and your teeth. Spent brass casings hit the floor. The smell was a combination of propellant gases, hydraulic fluid, oil, sweat, and fear. Heat was constant, and in summer conditions, genuinely dangerous. And then imagine sitting in all of that, knowing that the steel walls around you, The only thing between you and the outside world had limits. Knowing that a single infantryman with a disposable weapon standing in a doorway or behind a hedge could reach through those walls. When you understand what it was like inside, the decision to weld track links to the hull isn't just understandable. It's obvious. Of course you'd do it. Of course you'd grab anything that might absorb or disrupt an incoming round before it reached those walls. You'd grab sandbags, concrete, spare parts, anything. Because every centimeter of additional barrier between you and that jet of superheated metal meant the difference between walking away and not. Let's talk about where this was most critical. Because the track link modification, and improvisations like it, weren't equally widespread across all theaters. In the Pacific Theater, the primary threat to American armor was different. Japanese anti-tank capabilities were generally less sophisticated than Germany's, at least in terms of dedicated armor-piercing weapons. The Panzerfaust equivalent was less common. Japanese anti-tank tactics often relied on close assault, with soldiers literally clinging to tanks and attaching satchel charges or using suicide methods. The tank threat was also less severe, since Japan produced far fewer tanks than Germany. American modifications in the Pacific reflected these different threats. Additional protection against close assault, better perimeter awareness, working closely with infantry to prevent individual soldiers from getting alongside the tank. Track links appeared there too, but the context was different. In Europe, particularly in northwestern Europe, from 1944 onward, the Panzerfaust threat was overwhelming. Allied planners estimated that by late 1944, German infantry units were receiving Panzerfausts in the hundreds of thousands. Every German soldier potentially had or was close to one. Every hedgerow, every ruined building, every ditch was a potential launch point. In Italy, the terrain presented its own particular horror. Narrow mountain roads, ancient stone villages, tight valleys with no room to maneuver. The Apennines were not tank country. Vehicles had to move in column along roads where a single blocked or burning tank could immobilize an entire formation. Anti-tank ambushes in Italy were constant, and they exploited the terrain mercilessly. It was in Italy that some of the most extensive Sherman modifications were seen. Crews there had time to be thorough. Campaigns moved slowly through the difficult geography, and maintenance periods sometimes allowed for careful, well-welded additions to the hull. Italian theater Shermans were often the most heavily modified, covered in track links, spare road wheels, sandbags, and in some cases, improvised steel plates cut from other wrecked vehicles. The British and Commonwealth forces, fighting in the same theaters, did similar things with their Shermans and with other tanks like the Churchill and Cromwell. The British had a particular name for improvised external armor modifications. They called them appliqué armor when done formally, or simply extra kit when done by the crew. The logic was identical to what American crews were doing. The threat is real, the factory solution isn't here yet, and we are not going to sit inside thin steel and wait. Threats. There was also another dimension to this that doesn't get talked about enough, the psychological dimension. Sitting inside a tank that you believe is vulnerable is psychologically corrosive. It affects performance. It affects decision-making. A crew that's constantly aware that their vehicle might not protect them is a crew that hesitates, that doesn't push forward aggressively, that spends cognitive energy on survival anxiety instead of tactical awareness. Adding improvised armor, even if its protective benefit was debatable in certain specific scenarios, had a real psychological impact. It gave crews a sense of agency. They had done something. They had actively worked to improve their situation rather than simply accepting what they were given. That matters enormously in sustained combat. There's actually a well-documented psychological phenomenon in military history where soldiers, given some ability to affect their own safety, even a small one, even an imperfect one, perform better than those who feel entirely passive about their fate. The act of doing something, of problem-solving, of taking control of whatever variables can be controlled, is itself a resilience mechanism. American tankers who spent an evening welding track links onto their Sherman went into the next morning's fighting with something extra. Not just the track links themselves, but the knowledge that they had done everything they could. That is not nothing. In the context of brutal, sustained armored combat, that might be everything. Now let's talk about the enemy perspective. Because to understand why American tankers were making these modifications, you have to understand exactly what they were up against and what German anti-tank capabilities looked like from inside an M4 hull. The German military in World War II had what was arguably the most comprehensive and effective anti-tank capability of any nation at any point in the war. And they had it at multiple levels, from the largest tank to the individual infantry soldier. At the top end, you had the Tiger I and Tiger II. The Tiger I carried an 88mm gun, derived from the famous Flak 18 anti-aircraft cannon, a weapon originally designed to hit aircraft at high altitude and retasked for ground combat with devastating results. The Tiger's gun could penetrate the front of a Sherman at combat ranges that the Sherman's own 75mm gun couldn't reply at. Early variants of the Sherman's gun simply could not reliably penetrate a Tiger's front armor at normal engagement ranges. The Tiger was simultaneously better protected and more capable of killing at range. Encountering one was a serious tactical problem. The Panther was in some ways even more dangerous for a different reason. It was faster and more maneuverable than the Tiger, had a long and extremely powerful 75mm high-velocity gun, and its sloped frontal armor was very resistant to the Sherman's standard armament. American crews who engaged Panthers in Normandy quickly learned to aim for the side, the rear, or specific weak spots. Frontal engagements with Panthers were to be avoided, if at all possible. But these were the threats at the tank level, and tank versus tank encounters, while dramatic and deadly, were actually a subset of the total threat environment. More common, more widespread, and in many ways, more insidious, were the anti-tank weapons operated by infantry. The Pak-40 was the German Army's standard anti-tank gun by 1944, a 75mm towed weapon capable of penetrating the Sherman at most combat ranges from the front and at extended ranges from the side and rear. It was relatively lightweight, could be quickly emplaced, and was very difficult to spot when properly concealed. German crews were skilled at setting up kill zones, camouflaging their position, and waiting for Allied vehicles to enter their engagement envelope before firing. Below that, there were the shoulder-fired weapons. The Panzerschreck, a German copy and improvement of the American bazooka, was a reusable rocket launcher firing a shaped charge capable of penetrating 100mm of armor. It was effectively a German bazooka with more punch. A two-man crew could carry it, and it was common in German infantry units throughout 1944 and 1945. And then the Panzerfaust. By 1944, the Germans were producing Panzerfausts at a rate of hundreds of thousands per month. In a statement that tells you everything about the manufacturing scale involved, by late 1944, a German infantry platoon might have more Panzerfausts than it had rifles. They were single-use, disposable, and required almost no training. You pointed, you fired, and if you'd gotten close enough and hit a critical spot, you'd just destroyed a 30-ton tank with a weapon that cost a few Reichmarks to produce. In the urban combat of late 1944 and 1945, the Panzerfaust was ubiquitous. Every house might have a teenager with one. Every basement might contain a stay-behind unit with a dozen. American tankers learned to treat enclosed spaces as Panzerfaust country, to move through towns with infantry as close protection, and to scan every window and doorway. Even so, losses mounted. The scale of Panzerfaust production is worth dwelling on for a moment, because it contextualizes the entire improvised armor story. The Germans manufactured approximately 8 million Panzerfausts during the war. 8 million. Against that scale of shaped charge threat, American tankers were not being paranoid about protecting their hull sides. They were being completely rational. And track links were the rational answer, because of something we already touched on: the physics of spaced armor against shaped charges. Let me be more specific about why track links in particular worked well for this purpose, and not just any piece of metal. A Sherman tank track link was a substantial piece of steel. Depending on the specific type, a single link might weigh anywhere from 8 to 15 kilograms. It was designed to handle the mechanical stresses of a moving tank, which meant It was made from high-quality cast or pressed steel. It was dense, uniform, and crucially, it was available in large numbers, right there in the unit. When welded to the hull at a small standoff, typically just the thickness of the link itself, plus any weld seam, the links created exactly the right conditions to disrupt a Panzerfaust warhead's shaped charge jet. The jet would have to penetrate the link, cross a small gap, and then hit the hull armor. That transition, going through the link, expanding in the gap, trying to reform on the far side, was enough in many cases to significantly reduce penetration depth into the hull proper. It was not a perfect solution. A Panzerfaust fired at close range, perpendicular to the hull, with a clean hit, could still penetrate, but the margins were improved, and in armored warfare, margins matter enormously. There were also practical limits to how many links crews could add. Weight was a constraint. The Sherman was already operating at or near its designed weight limits. Adding too many track links, especially on the front hull, where the suspension had to handle them, could strain the drive system, affect the transmission, and reduce the tank's mobility. Some commanders set informal limits on how much improvised armor was acceptable. Others let crews use their judgment. Track links also had the advantage of being easy to mount in a variety of configurations. Crews could attach them flat against the hull for maximum coverage. They could hang them at angles for better deflection. They could concentrate them on specific areas, the hull sides being most common, rather than trying to cover everything. The modularity, if you can call it that, of individual links allowed crews to work within weight and space constraints in ways that a single large plate of steel would not. Other types of improvised armor were also used, and it's worth discussing them briefly to give a complete picture of how creative American tankers were in addressing their vulnerability. Sandbags were one of the most commonly improvised additions. Sand doesn't sound like armor, but against shaped charges, sand is actually quite effective. Dense, granular material is remarkably good at disrupting the jet of a shaped charge warhead because the individual grains absorb and scatter the jet energy rather than allowing it to travel in a coherent stream. Multiple armies discovered this independently during the war. The problem with sandbags was that they were heavy, they degraded in rain and use, and they were awkward to mount securely on a tank hull. Concrete was used in some units, particularly in Italy. Crews would pour concrete against the hull sides and let it harden, creating a solid layer of masonry outside the steel. Concrete is cheap, available in ruined buildings, and reasonably effective at disrupting shaped charges, but it was extremely heavy, and adding it reduced mobility significantly. It also cracked and fell off, with the vibration of tank movement and shell fire. Concrete modification was not widespread, but it happened. Wooden planking appears in period photographs as well. Wood is much less dense than steel or sand, and offers almost no protection against a kinetic penetrator or a full-power shaped charge. But thin wood, placed at a standoff, can in some edge cases catch the fuse of a Panzerfaust warhead and detonate it slightly prematurely, before the jet is optimally formed. This was marginal protection at best, and crews who used it likely did so as much for the psychological comfort as for any reliable ballistic benefit. Some units acquired steel plates from wrecked vehicles or even from industrial sources and welded them to the hull. This was closer to formal applique armor and worked similarly to the track link approach, though plate steel cut from a wrecked vehicle might not be the same quality as the specially treated steel of the hull or the track links. The Army actually took note of what crews were doing and eventually moved toward more formal solutions. The Armored Fighting Vehicle Board and various Army Ground Forces commands received field reports about crew modifications and took them seriously enough to investigate. The M4A3E2, the so-called Jumbo Sherman, was a factory-produced tank with significantly thicker armor, up to about 100 millimeters on the front hull, and a heavily armored turret. It was specifically designed for assault roles where resistance to direct fire was paramount, but it was produced in very limited numbers, fewer than 300 vehicles, and couldn't be provided to every unit. More broadly, the Army was already developing what would become the M26 Pershing, a genuine heavy-medium tank with a 90mm gun and much thicker armor. But the development and production pipeline couldn't keep up with operational demand. The Pershing arrived in Europe in February 1945, just months before Germany's surrender. Most Sherman crews never saw one. In the meantime, track links. It's also important to talk about the officer chain of command's role in all of this, because the story isn't simply, crews did this, Army didn't care. The relationship between improvised modifications and official authorization was complicated and varied. In some units, company and battalion commanders actively encouraged their crews to add improvised armor. These commanders were close enough to the fighting to understand the vulnerability, and they were pragmatic enough to recognize that anything which kept their men alive was worth tolerating, even if it was technically non-standard. Some maintenance officers facilitated the work by providing welding equipment and guidance on where modifications could be applied without compromising critical systems. In other units, there was resistance. Some commanders worried about the weight impact on the tank's automotive systems. Others worried about non-standard modifications complicating maintenance. A few were simply rigid about following regulations, which did not authorize crews to weld materials to the hull. This tension was real, and it played out differently in different divisions and regiments. The 4th Armored Division, one of the most experienced and effective American armored formations, was known for aggressive improvisation and had commanders who tolerated and even supported crew-level modifications. Other units were more conservative. At the Army level, there was genuine ambivalence. Official technical manuals didn't authorize the modifications, but field reports repeatedly confirmed their value, and no one at the senior level moved to formally prohibit the practice in a way that was enforced. The result was an informal acceptance. Don't make it doctrine, but don't court-martial anyone for doing it either. This kind of informal pragmatism is actually very characteristic of American military culture in World War II. The United States Army was not a rigid, top-down organization in the way that some other armies were. American soldiers at all levels were encouraged to show initiative, to problem-solve, to improvise. The Army's overall approach to the war emphasized adaptability and speed. In that culture, a tanker who figured out a way to improve his vehicle's survivability was, at some level, doing exactly what he was supposed to be doing. Let's also address a common question about whether the improvised armor actually worked, because the answer is more nuanced than a simple yes or no. There are documented cases where improvised armor, including track links, provided measurable protection. Crews reported that impacts to track link-covered sections of the hull that would otherwise have caused penetrations instead failed to penetrate, or penetrated with significantly reduced behind armor effect. Post-battle damage assessment of recovered vehicles sometimes showed clear evidence of Panzerfaust strikes on external armor that had not fully penetrated the hull. There are also cases where improvised armor made no difference. A direct, close-range Panzerfaust hit on a heavy, properly welded section of hull side might penetrate through track links, through hull armor, and still produce a lethal behind armor effect. The improvised armor was not a guarantee, it was a probability improvement. The physical testing done by Army and Allied ordnance teams during and after the war confirmed what field experience suggested. Spaced armor, even informal varieties, did reduce the effectiveness of shaped charge warheads significantly. The standoff distance available with track links was admittedly small, typically only a few centimeters. Formal spaced armor systems, designed by engineers, used larger standoff gaps for better effect. But even small gaps provided some benefit, and some benefit was vastly better than none. The statistical picture, looking at casualty data and loss rates, is harder to interpret. You can't run a controlled experiment in combat. Vehicles with improvised armor and vehicles without were both being hit, often in different circumstances, different terrain, different engagements. Isolating the variable of improvised armor against all other factors is essentially impossible from historical records. What we can say is this: the men who added track links to their Shermans were not wrong to do so. The physics supported it. The field reports supported it. The logic was sound, and the fact that it became so widespread, in so many units, in so many theaters, suggests that the crews themselves believed it made a difference. Men in combat are not inclined to do things that have no practical value. They're too busy for that. If track links were being welded onto hulls all across the European theater, it's because the people in the best position to judge The men inside those tanks concluded that they were worth the effort. Now let's put all of this into the broader context of what it tells us about World War II armored warfare, because the track-link story is really a window into something larger. The war in armor was fundamentally a war of adaptation. No nation entered the conflict with weapons that remained unchanged and adequate throughout. Everyone modified, everyone improvised, everyone struggled to keep up with the evolving threat environment. The Germans went from the light Panzer I and II of the early war to the massive Tigers and Panthers of 1943 onward. The British went through Matildas and Cruisers and Churchills and Cromwells and Comets, always chasing better protection and firepower. The Soviets took the T-34, already one of the best tanks of 1941, and spent the entire war improving it, adding better guns, better armor, better engines. The Japanese, with a weaker industrial base, largely failed to keep pace and paid for it in the Pacific. The Americans improved the Sherman throughout the war, from the original 75mm armed variants to the 76mm armed M4A1 and M4A3 models, to the wet stowage improvements, to the HVSS suspension on late models that improved flotation and reduced ground pressure. But the improvements always lagged behind what the field demanded, partly because of the Army's strategic philosophy and partly because of industrial inertia, the difficulty of changing production lines that were already running at maximum capacity. And in that lag, between what the factory produced and what the field needed, the track links lived. They were the tangible evidence of a gap that the Army acknowledged in part, addressed incompletely, and that individual crews were left to bridge with whatever they could find in the motor pool. There is something very American about that solution, not waiting for the bureaucracy to catch up, grabbing what you have, applying what you know, and making it work. The Sherman tank with improvised track-link armor isn't a symbol of failure. It's a symbol of a kind of practical, determined problem-solving that characterized so much of the American military experience in World War II. These crews didn't complain into a void. They acted. They looked at their tools, looked at their threat, looked at the physics between them, and found a solution that worked well enough to be worth doing. And then they drove that improvised machine into battle and did their job. It's also worth noting that the Germans, facing their own shortages and shortfalls in 1944 and 1945, were doing exactly the same thing in reverse. German tank crews applied Zimmerit paste to their hulls to prevent magnetic anti-tank mines from sticking. They hung spare track links and spare road wheels on the outside of their tanks too, often on the side skirts of Panthers and Tigers. They added additional armor plates in improvised ways. The common experience of men deciding that their factory-provided protection wasn't quite enough and going to find more transcended nationality in World War II armored warfare. The specific tools were different. The specific threats were different. But the human impulse to take control, to do something, to not accept passively what fate and the factory have assigned you, that was universal. Let's talk about what happened after the war, because the story of improvised spaced armor didn't end in 1945. The lessons of World War II shaped every tank development program that followed. The vulnerability of tanks to shaped charge weapons, as demonstrated so dramatically by the Panzerfaust on one side and by early bazookas on the other, drove engineers to think seriously about how to defeat the shaped charge threat without simply adding more and more solid steel, which made tanks impossibly heavy. The answer